Good morning, everybody. How y'all doing? Today, we are going to dig into how and why things change phase. So last time we looked at what a solid, what a liquid, and what a gas is, but we looked at it a little more detail than than you did in the past, right? We looked at energies, we looked at intermolecular forces of attraction and what the particles are doing. And so as we look at phase change, as we look at what causes something to go from a solid to a liquid to a gas and a gas to a liquid to a solid and vice versa, it can also go from a solid right to a gas and from a gas right to a solid. We're going to look at it from two perspectives, right? We want to look at what's happening to the particles in terms of their motion and their position relative to one another. In other words, how close or how far apart they are to one another. But we also want to watch what's happening to the energy, right? Because either adding energy or taking away energy, like a change in energy is really what makes or drives phase change. It's what makes phase change happen. Are you guys picking up what I'm putting down there? So that's what we're going to look at. We're going to look at what happens during a phase change, both to the particles of our sample and to the energy of our sample. So that's what we're looking at. Are you ready? All right. So phase change. Why? Why phase change? Well, I'll tell you why. Because energy has been added or taken away. So what I'm going to go through here is what happens when we add temperature, right? So this is adding heat, but everything that I'm going to talk about goes exactly the same, only in reverse when we remove heat. Got it? So adding heat energy, Q, joules, whatever, it increases the temperature of your sample, right? And the greater temperature means that those particles are colliding harder and they're colliding faster. So the faster they move, they slam into each other harder and harder and harder, right? And just like if we're playing pool, if you hit the cue ball really, really hard, right, they are going to rebound farther apart, right? Like they're going to bam, bounce off of each other harder and harder. And when they rebound and get taken away and apart from one another, dude, that really affects their ability to hold on to one another. It affects those intermolecular forces of attraction, right? Because the greater the distance you have, that means less intermolecular forces of attraction. So heating things up makes the particles move faster, they collide harder, and they rebound farther apart. And that further rebound, the more distance between the particles, that causes the intermolecular forces of attraction to drop, 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 drop. Are you guys getting what I'm saying? Now, this goes until you hit this magical point where when these intermolecular forces of attraction are weak enough, the distance greatly increases. Right? So all through here, when we're adding heat and things are going faster and faster and faster, when they collide further apart, in terms of atoms and molecules, the space isn't really breaking apart too much, but it's like the springs are still holding them together. So it's not like they're bouncing pretty far off of one another, because those intermolecular forces of attraction are still holding them. It's like springs holding the particles together. However, they're still pulling on those springs pretty hard, right? And those springs are the intermolecular forces of attraction that stick those particles back together. However, there comes a point when these particles rebound out so hard that they kind of overcome the force of those springs or of those intermolecular forces of attraction. And when that happens, when those particles can sort of pull apart those bonds and actually physically move apart from one another, that's where we have this really trippy thing called a phase change, where solids melt, liquids vaporize. And then we have the exact same thing in reverse. As we cool things off, they slow down. The particles start to slow down. As the particles collide slower and slower, their rebounds become weaker and weaker, and those springs take over and pull those particles together. And that's when we have phase change from something like a gas to a liquid or a liquid to a solid, where the intermolecular forces of attraction sort of take over. Are you guys picking up what I'm putting down there? I certainly hope so. Oh goodness, it's still early for me. Now look, this is the thing. temperature does not change during phase change. Did you know that? Nope, nope, nope. Temperature does not change during phase change. It is a trippy thing, but dude, think of it this way, man. Let's say you're about to make some spaghetti, because who doesn't like spaghetti? Everybody likes spaghetti. Of course you want to make spaghetti. So you go and you like put a pot of water on the oven or on the stove, and you light it up, and it starts boiling. Well, my question for you is, what temperature does water boil? In Celsius here, because we don't do that Fahrenheit garbage around here. Right, yeah, 100 degrees. Water boils at 100 degrees Celsius, okay? So let's say something happened, and I don't know, you go over into that room over there, not where the boiling water is. You go over there, and I don't know, maybe you get into an argument with somebody, maybe, I don't know, you get distracted by something, whatever, and you come back like 15, 20 minutes later, and the water is still boiling on top of the stove. Now I'm going to ask you, what temperature does water boil? It boils at 100 degrees Celsius. It doesn't matter that you left and came back 20 minutes later. Water still boils at 100 degrees Celsius. So while water is boiling, it's 100 degrees, and that's pretty much it. It doesn't change. Yes, there is fire underneath the water, and it is putting heat into the water, but the temperature of the water while it's boiling doesn't change. What? Well, it's true if you put a thermometer in there. The thermometer will basically just stop once it starts boiling. And here's why. Here's why. Now, this happens only during phase change, right? So what happens is the heat energy that you're adding, or in case you're cooling, that you're taking it away, it has no effect on the kinetic energy. In other words, the heat that you're adding, if you're heating something up, it's not making the particles move any faster at all. Instead, what's happening, there is a change in this. There's a change in the down here. There's a change in the potential energy, okay, of those particles because of a change in the distance between the particles. So during phase change, the energy that you're adding is not going to make the particles move faster. It's going to make the particles further and further apart. I hope that makes sense. Because, I mean, that's like adding potential energy. And there's a lot of potential energy in, something that has a different phase. Like, if you go from water to steam, man, there's a lot of energy. They used to run trains on steam. That is a lot of potential energy right there. I mean, we've all seen, there's an enormous amount of stored energy. So if you boil water and turn it into steam, that steam has an unbelievable amount of energy stored within it. Why? Because of the distance between particles, because of the particles' positions, right? Because we know that different positions of things can cause something to have more or less potential energy. A rock at the top of a hill, or a boulder at the top of a hill, has more potential energy than the boulder after it rolls down the hill and is in the valley. There's less potential energy in that rock. Why? Because of its position. You dig what I'm saying? So during phase change, temperature stays locked. It does not change during phase change because all of the energy goes into the potential energy. Right? So all the heat energy that you're adding is converted to potential energy by moving the particles further apart. So kinetic energy stays exactly the same because there is no temperature change, and we have an increase in potential energy if you're heating. Now the same thing, only opposite, if you're cooling it, there is a decrease in potential energy. Right? But still, the temperature remains exactly the same during this phase change period. You got it? And I'm not lying, man. You can go try this at home yourself. It's pretty easy. And so what this gives us are two things. We have freezing and melting point. Now, I'm calling it freezing melting point, right? It is both freezing and melting because it's all a matter of perspective. The question is, what temperature does water freeze? Well, water freezes when it's 0 degrees, right? And you're taking energy out. It hits 0 degrees, like you're cooling water. Water cools. It hits 0 degrees. As long as you keep taking energy out, that water is going to freeze at 0 degrees. Awesome. Now that water, let's say it's out on the lake, it gets to -10. So now the ice is -10 degrees. It's a solid chunk of ice, really good and blocky. And now we're going to heat it up. And that block of ice goes from -10 to -9, -8, 7, 6, -5, -4, -3, -2, -1. It hits 0, and we're adding heat. What temperature does it melt? Well, water melts at 0. So 0 is that place where it's that place where both melting and freezing can happen. It just depends on if you're taking energy in or taking energy out. Energy in or energy out. That's what determines whether it's like freezing and melting. And it is defined as, like the way that we define freezing point or melting point is the temperature at which a solid and a liquid exist in equilibrium. In other words, so what this means, so equilibrium, it's like the fancy word for homeostasis. It's like all nice and steady. So theoretically, if we had this like pretend, I don't know, freezer that could hold things exactly 1,000,000% 0, and you had a glass and you filled it with, I don't know, 5 grams of water and 5 grams of ice, you put it in that perfect 0-degree temperature container. When you came back 100 years later, there'd be 10, what did I say, 5 or 10? Well, if I started with 5, you end with 5. There would be the exact same amount of ice as there is water. Doesn't matter how long you wait, because when it means that once it hits equilibrium, every time one little thing freezes, one little thing melts. It's like just kind of stuck in the middle. Can't do either one. And that gives us a new fundamental property of nature called heat of fusion. Now, fusion is sometimes referred to as like the freezing process. Like when things stick together, right? They fuse together. But then it's also melting when you unmelt them, so it's heat of unfusion. I don't know. It's called the heat of fusion. And what it is the amount of energy it takes to melt 1 gram of a substance, right? So heat of fusion is the amount of heat or the amount of energy needed to change 1 gram of a substance from liquid to solid. I said liquid to solid. I meant solid to liquid. That's the heat of fusion. Well, actually, it doesn't matter. Solid to liquid, liquid to solid. If you're going from a solid to a liquid, that means you're putting the heat in. And if you're going from a liquid to a solid, that means you're taking the heat out. It's the exact same. So for water, it's 333.6 joules per gram. So what that means is if you want to melt 1 gram of ice, you got to put in 333.6 grams, and then you'll get water. However, if you have 1 gram of water, you got to take out 333.6 joules in order to freeze it. That's assuming that we're at 0 degrees. You guys picking up what I'm putting down? Riding away? Feeling the flow? Awesome. Because the other fundamental property of nature is like the heat of vaporization. But before we even get there, we got to talk about something trippy. It's this, the vaporization and condensation. If you'll notice up here, freezing and melting is the freezing melting point, I just set a number, right? It's like, oh, it's 0, right? Because that's where freezing and melting happen at the same, like that's the temperature where freezing and melting happen. Can't really say that for vaporization or condensation. Now, vaporization, that's going from a liquid to a gas, and condensation, that's when you go from a gas to a liquid. But what we can say is that the boiling point is the temperature at which the vapor pressure equals atmospheric pressure. It's not a fixed temperature, unfortunately, because the atmospheric temperature or the atmospheric pressure can change with the weather, and that means that the boiling point can change. So what is the boiling point of water? It depends. Now, at perfect conditions, at like exactly 1 atmosphere of pressure, and if we put everything perfectly right, like we would in a lab, we can say that pure water boils at 100 degrees Celsius. You got it? And the reason why is because at 100 degrees Celsius, the water's vapor pressure, right? Vapor pressure, and that is the pressure that the particles of that water are exerting on the container and pushing up on the air that the water is in contact with. Because if you think about it, you have you got like a surface of water over here, right? Here's a surface of water inside of a cup or something. But there's like a little atmosphere atoms and things, like coming down and slamming into the water and bouncing off, and coming in and slamming and bouncing off, right? Because there's air on top of that water sample. And it's not just a little bit of air. It's a column of air that goes like from here all the way to outer space. That entire column of air is swishing down on that sample. And it's actually quite a bit of pressure. You and I don't notice it because we were born here and we've lived here, like on the surface of the earth. So we're not really aware of the pressure that the atmosphere exerts on us. Man, it is there, right? It's why our ears pop when we go like high up onto a mountain, or if like we drop down really, like go from a high up to a mountain and down low, our ears pop because of the change in atmospheric pressure. Also, not for nothing, if you look on the back of some cake mixes, they'll like give like cooking directions, then they'll say, but for high altitude, do this. Because if you live in like Denver, Colorado, you're a mile up from sea level, and boiling does not happen like the way it normally does that high up, like not at the same temperature. So to make something boil, we got to get the vapor pressure. We got to get the thing's vapor pressure, right, to push hard enough, right? So this little water particle needs to push when it hits the surface hard enough to break free from all these like atmosphere particles coming in and like smacking down onto the water. So this little water particle needs to hit so hard that it can blast past all those like all that pressure from the atmosphere and rise up. And once it does have enough like force to do that, you'll notice that like little bubbles will start to form, right? Because those particles are able to push. They're hitting so hard and rebounding so hard that they're able to push away and push apart and push against that atmosphere to make it boil. So what that means is if we didn't have an atmosphere, water would boil at a much, much, much colder temperature, because it's the atmosphere that's kind of squishing everything down and squeezing the particles together into the liquid phase. And so, oh yeah, and also I should say this, I almost forgot, sorry, that vapor pressure, or the force that the particles exert on their surroundings, it like increases with temperature, right? That means that the hotter something gets, the faster the particles are moving, the harder they smack up against the side of the container, the greater the force that they can exert, either on the side of the container or up on the atmosphere that's like pressing down on it. You guys get what I'm saying? And so now we can dive into this thing that's called the heat of vaporization. Now the heat of vaporization, right? If you can guess, it's the amount of heat you need to like vaporize something. It is the energy needed to change 1 gram of a substance from liquid to a gas. And now here's the kicker. It must be at constant temperature and pressure. Well, of course it's going to be constant temperature because it's a phase change, but boy oh boy is that important. 1 atmospheric pressure. Because as soon as you change like the atmospheric pressure, you're going to change the temperature and all other kinds of things that will change. So for us, at exactly 1 atmospheric pressure, and let's pretend everything is perfect, so it's 100 degrees Celsius, it'll take 2,259 joules of energy to boil 1 gram of water, or to vaporize. Boil, vaporize. You know, tomato, tomato. You guys picking up what I'm putting down there? This vapor pressure thing, the boiling point's just stone cold trippy. So you can literally boil warm water. So you and I live in the normal world. And so to make water boil, we have to get the water hot, because the atmosphere is pretty much the same, right? However, if we could change the atmosphere, like if we had a little vacuum chamber, you could take like warm water, and you can boil it by removing some of the atmosphere and removing that like atmospheric pressure. So vapor pressure and atmospheric pressure have to be exactly the same. And we are used to like needing to increase the vapor pressure to make boiling happen. However, if the vapor pressure is way down here, if you have a vacuum chamber, you can take the atmospheric pressure and lower it until the atmospheric pressure matches the vapor pressure. Boil, and you can boil warm water. It's the weirdest thing that I've ever seen. Oh yeah, 2 other words, 2 things we need to know. Deposition. Deposition, this is where a vapor goes directly to the solid phase. It skips liquid, just like vapor, solid. We see this all the time. we call it frost, right? So when you wake up in the morning and everything's covered with like little crystalline, like frosty, beautiful crystals of water, it's because the water vapor from the atmosphere like bumped up to something that was really cold and just stuck because it lost all of its kinetic energy and went straight to a solid. That is what causes frost. Frost is deposition. Now the other one, this is called sublimation. Sublimation is where something goes from a solid directly to a gas. Now this you'll see in the spring where like usually in April we'll have like a snowstorm and then like a really nice sunny day and you can just see the vapors like steam like wafting up out of the snow, and that is sublimation. It's where it gets so warm and just right that it just breaks off and floats away into the atmosphere. Also, if you've ever noticed, if you leave ice cubes in your freezer for too long, they'll often sometimes start to shrink and get like kind of weird and like smaller, little weird stuff on it. It's because that the water, the ice cubes, is sublimating inside your freezer, because your freezer like does a defrosting thing, so it doesn't get frost all over the place, and that helps promote sublimation. So that's it, guys. Except for this, we got to look at this thing. Well, it's going to be a thing in a minute. What I'm going to draw here is going to be a heating curve, right? And the up and down, I guess that's the x. Is that the x? No, that's the y. The up and down one, this is temperature. So the higher up we go, the greater the temperature. And this from left to right, this is going to be time, right? And so what I'm going to do is I'm going to take a sample. I'm going to take its temperature right here at time 0, and I'm going to heat it, right? So it's a sample of something, and we heat it. What happens to the temperature over time as we heat it? Well, as time goes on, temperature goes up until all of a sudden we'll notice that the temperature will stop rising. And the reason the temperature is not rising is because that sample is going through some kind of phase change, right? And at some point, that phase change is going to be done, and then the temperature will start going up again. And then as time goes on, we're heating, it goes up, 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 it goes up, 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 heat, up, until all of a sudden, again, the temperature will stop increasing. It's supposed to be a straight line, just work with me. It'll be a straight line until all of a sudden it stops being flat and the temperature goes up again. Does that make sense? I mean, do you guys kind of follow what's happening with this thing? And so this is what's called a heating curve. This is what happens with the temperature of a sample as you start out from a solid, go to a liquid, and go to a gas. And what we need to know about this graph, there are a couple of things. One, we need to know the phases. We need to know the phases of the graph, and we also need to know what's happening with the energies. It's going to be kinetic energy, and it's going to be potential energy. Okay? For each segment of this graph. And this is what they often do is like we're at these junctures, they'll like give them numbers or something. So I'll call this A, I'll call that B, C, D, E, and I'll call that F. And for each one of these, we need to know phase, we need to know what's happening with the energy. So let's start with the energy. Right here on this graph, on this portion of the graph, on portion AB, what is happening to the potential energy and what is happening to the kinetic energy? Well, let's think about it. If this line is going up, that means the temperature is going up. And temperature is the measure of the average kinetic energy. So that means the kinetic energy is going up. If temperature goes up, kinetic energy goes up. Because temperature is measuring kinetic energy, right? So, if all the energy is going into kinetic energy, right, the line is going up, that means the potential energy is just going to stay the same. Nothing is happening there. You dig? So that's what's happening. Line goes up, kinetic energy goes up. Potential energy stays the same. Now, in this line segment between B, C, right, what's happening with these energies? That's what's happening with potential energy and what's happening with kinetic energy here. Well, if you notice, this line is not going up. It's staying steady. It's staying the same. So if the temperature is staying the same, that means kinetic energy is staying the same, right? So kinetic energy is staying the same, but we're still adding heat to it. We are still adding heat. So where's that energy going to? Well, during a phase change, we know it's all potential energy, and this is kind of our evidence, right? We're adding heat to it, but temperature stays the same, so it must be going into potential energy. You guys dig what I'm saying? Now for this line segment right here, line segment D or CD, potential energy and kinetic energy once again. Well, if the line's going up, that means temperature's going up. That means kinetic energy has to be going up. And if kinetic energy is going up, potential has to stay the same because all the energy is going into kinetic energy. Now we've got yet one more line segment between D and E. And we're going to look at potential energy and kinetic energy one more time. And this one, once again, is perfectly flat line. And so, if the line is not going up, that means temperature is not going up. If temperature is not going up, kinetic energy is not going up. It's staying the same. That means potential energy is the one that has to be going up. Then over here, finally, we have a line going up. That means potential energy is staying the same, and kinetic energy is increasing because the line is going up. You dig what I'm saying there? Certainly hope so. So those are the energies. I started out with the second one first, because why wouldn't I do something like that? I don't know. Okay, now for phases. So we are only going to be looking at solid, liquid, and gas. All right, and if it's starting out at the coldest, goes through a phase change. And so here's our second phase, goes through a second phase change. There's our first phase change. This is going to have to be solid during AB, right? Now here, because it's going to be the process is going to be called melting, right? So when things melt, you have both solid and liquid. You have both solid and liquid during this phase change until you get to right here. Now at this point between C and D, it was solid down here, melted here. During this section, we have all liquid, right? Until the liquid gets so hot that it starts to boil. And in this line segment between D and E, as it's boiling, you have in the same container, you have liquid, you have both liquid and gas phase, right? During this section here. Because this, it's like a pot of water with little bubbles in it, right? The bubbles are the gas phase. And then here, finally, this is all gas. You guys dig what I'm saying there? So those are the things. Oh, hey, one other thing that we should talk about here are what are these phase changes be like what are they called? Like what do we call these phase changes? So if we're going this way, right? If we're going from a solid to a liquid, we call that melting. Right? However, so like we're going melting this way. However, if we're going this way, we just have to do this way up here, that's freezing. Right? If we go from liquid to a solid. So solid, we melt. Now we have a liquid. As we change from a liquid going this way to a gas, I'm going to call that one vapor, or let's just call it boiling. Because it's easy. And then that's it. We're not going to go what's past the gas. That's gas. Same thing, only completely different. If we're going from a gas to a liquid, that is condensation. So if it is cooling and going that way, we call that condensation. That's like when you have a big glass of like lemonade or Kool-Aid and it's hot and it's summertime, right? Like mid-August. And like the outside gets little like droplets of water. That's like the humidity or the water vapor in the atmosphere hits the glass and just changes right into a liquid because it gets so cold so fast. That is condensation. But there are two more. When we go from a gas directly down to a solid, we call that, remember this is frost, that is deposition, right? From a gas to a solid. And then if it goes from a solid through my face to a gas, We call that sublimation. So we've got 3 phases: solid, liquid, gas. We've actually got 6 phase changes. If you're heating, it's going to be melting here, right, between solid and a liquid. Between a liquid and a gas, we're going to call that boiling or vaporization. Now, if you're cooling it and things are going like the opposite direction, if you're going from a gas to a liquid, that's condensation. And then if you're going from a liquid to a solid, we call that freezing. But there's also sublimation and there's deposition. So there's like 6 phase changes. There's 3 different phases, and in each part of this graph, line segment, if you will, we need to know what's going on with the potential and kinetic energies. And anytime the line goes up, that means kinetic energy goes up. Potential energy has to stay the same. If the line is staying flat, that means temperature is staying the same. That means kinetic energy is staying the same. Potential energy is the one that's increasing or decreasing if you're cooling. And here, same thing with this one. Line goes up, kinetic energy goes up. Line goes flat, kinetic energy stays equal. Line goes up, kinetic energy goes up. Got it? If kinetic energy is going up, potential has to stay equal. If there's no change in kinetic energy, that means potential has to be the one that's changing. Are you guys picking up what I'm putting down? Certainly hope so. I don't doubt it one bit, but we will be spending a little bit of time wrapping our brain all the way around this graph and all the amazing stuff that is contained sort of like in there, over there, in that thing. And also, man, we also need to spend a little bit of time looking at things boil, because it's actually a little bit more complicated than you might think. It doesn't just happen at like one temperature. All right, we're done. Phase change. Have an awesome day.